someone that has no idea what they're getting a service on a is not even introduce ourselves a little bit more, what we do, and then maybe moderate a bit of discussion. But just feel free to interrupt us, ask questions to us or Bob, and we'll just take it informally, I think, from here. So, as Reza said, I'm Roger Melko. I'm a professor at University of Waterloo, associate faculty at the Perimeter Institute for Theoretical Physics, and my specialty is simulating quantum mechanics. So, what Bob said, basically one of the sort of main applications that maybe Feynman originally talked about a quantum computer doing, simulating quantum mechanics. What we do is simulate quantum mechanics as good as we can with classical computers that exist today. Part of our simulation suite, or our simulation techniques, are simulating quantum computers, or at least the building blocks thereof. So, Peter?
I'm Peter Widak. I'm an assistant professor at the University of Toronto. I'm looking at applications of quantum computers, particularly these early quantum computers that we have, say now and the next 5-10 years. And I'm particularly interested in machine learning and AI, whether there's anything to gain there. And so why don't we start with a couple of questions? Roger?
Ask me a question.
You ask a question from the government.
Well, I want him to finish eating first. So.
No.
Peter, I can ask you a question. I like the idea of quantum volume. It's I guess I was used to thinking of quantum volume as like it's this volume of the circuit, but it's not just the volume of the circuit; it's the volume of number of qubits and error correction. Do you think that the scaling of quantum volume will follow something like Moore's law?
I think we hope. Let's put it this way. I think so. When I was stuck in the snow, I kept thinking, but there's pizza, so. Sorry. If you look at last year, so 2017, just take kind of our story. We started the year, we had 5 qubits, it was 16, and it was 20. We said we had a 50 qubit. This year we said nothing was over qubits. So part of the question is, if you just did a simple graph of the number of qubits versus time, it's a step function. So pick whoever you want. You're going to be sitting at a certain number of qubits for a certain time, but you're busy. And so all the parameters you mentioned, so you're trying to sort of error. Sometimes you're just doing engineering, right? You need a larger horizon, and you're trying to get the cooling curve. So I think so. It's going to be a step function. I don't think it's going to be quite as even as Moore's law was. I think you'll see a few years where yes, you might get this kind of doubling, and then for 2 or 3 years it slows down, and then it kind of jumps really up. So I think of it as kind of an interpolated exponential function, a step function.
So many of us who work in artificial intelligence are used to the AI concept of AI winter. Do you foresee any quantum computing winter?
Well, you have multiple AI. Well, maybe not. No, I actually started in symbolic computation. And so years ago, that's why I came up with this Moore's law.
Yeah.
You get these things like that. And they threw us out of it. We were AI for a little while, but then they threw us out. It is a concern. I think we have roughly 2 to 3 years as an industry to really start showing something significant, right? And so what I call quantum advantage. Otherwise, you've got a lot of explaining about what's really happening. So even this notion about quantum volume, to make sense to a lot of people, what is a qubit error rate and what it depends on, right, is tricky. I mean, how do you tell a general audience just how many qubits? Go, how many qubits? Oh well, it depends on your readout fidelity. They don't care. and things like this. So I'm trying to avoid a winter, and that's what I was talking about, the Valley of Despair, right? That's what would be our winter.
I can ask questions all day.
Can I have one?
You have one.
Yeah, so years ago I had no idea what a wave function was, and I was as happy as a worm. Since then it's been downhill. And so now I'm involved in educating a large number of people about quantum computing, and I explore different libraries and frameworks to see what's the best fit. And it's really confusing to get started. There's so many Hermitian things in quantum mechanics, and you get confused, like what's a measurement, what's Hamiltonian, both Hermitian, and all this stuff. So I find that well-written software and well-documented software can help a lot. And so I've seen that the Quiz-Kit came a long way over just the last couple of months, and I wonder, like, what do you plan to improve the framework itself as well as documentation?
We do have a very big project going on right now to improve documentation from start to finish. We publish a roadmap on the site, so there are some things that I forget. One of what I think is a very interesting area, so is the notion of compilation, right? Or they call transpilers, transformative compilers, things like this. So when a lot of these things we talked about, like we're ancient history, it was like June of 2017. When you write a program, you would have a particular device in mind, and you'd say, well, qubit 2 do this, and qubit 3, and it was literally that qubit and that device. And now we've already virtualized this to that extent. So you might say, okay, well, give me 3 qubits and 3 classical registers. You figure out what you want. But when you get a much more sophisticated algorithm, there is really this notion of compilation. So with the quantum computer, you're playing off, among the things, the number of qubits, which is important to do bits, but also the depth of the circuit. So modern quantum computers are not perfect or logical quantum computers. It doesn't make any difference whose, but a given qubit only has a certain lifespan, whether it's inference time, a given operation takes a certain amount of time, has errors to it. So how many things can you do to a qubit? So therefore, when I'm mapping an algorithm to an actual quantum device, it's to a directed acyclic graph. And so that represents the device. Sometimes a given qubit isn't feeling that well today. The error rates are really high, and I compile it. What does it mean to have an optimized compiler? So the transpiler infrastructure is going to, I think it's the next release, is going to be much more front and forward for people who can essentially their own tasks. I do think, university professors, I think there are many masters and possible PhD theses now that aren't even physics. That is, I think a lot of computer science is going to reopen. Optimizing compilers for classical computers. So I think the next 10 years will be
I'm more interested on the practical application. I mean, like a proof to the society that using quantum computers gives some benefits. I was reading about protein unfolding research, or fertilizer, or Microsoft with their topological quantum computer. When they have a development environment, they said they have some progress made in this area. You show so many startups, using your platform and stuff. So what they do they have, like, do you have practical example of success stories where the quantum computer indeed helped solve some problems that benefit society?
This is the real downer part. So quantum computers today simply are not powerful enough to do things better than a classical computer. We're very honest about this, and that was my 3 to 5 year period. So So it will only be when we reach this quantum advantage phase, right, where we can say there's significant difference. And, we often get this question from commercial clients, right? So some commercial clients, they say, well, look, it's going to take 3 years. Make an appointment with my assistant and come back in 3 years, right? And others, right, in some industries say, I got to get going on this. What sort of people should I hire, right? I have to start thinking about this. And they're not hiring 25 people, but they're hiring like 2 people. There was an article in the New York Times 3 weeks ago about the shortage of quantum physicists, right, to go into this industry. So we really can't, and just to really, not believe, you can very nicely emulate a 20-qubit quantum computer on your smartphone right now. That's the way it is, right? But we are working at building larger machines, and we are really spending a lot of time on the so-called short-depth circuits, understanding what you can do with circuits where you have limited coherence time. You only have so much time to do this. There's been a lot more progress on that than I think a lot of people expected. So that one scientific result I showed was that, but other algorithms as well. That people do.
Hi. I'm not a physicist, I'm not even a mathematician, so you have to bear with me. I'm interested in the engineering behind building a quantum computer. There's a lot of hardware control behind this to make it work, and very complicated, complex hardware, and we talk about this hybrid between a quantum computer and the classical ones. How do you see the hardware development evolve? Does it get smaller? Does it get miniaturized? Or where does it go from here?
So we do a particular qubit technology called superconducting transmon qubits based on Joseph's injunctions. It was, people have known about Joseph's injunctions for a very long time, exhibiting quantum behavior. In other forms, they're used in quantum sensing, things like that. There are other ways of doing it. There are photonic approaches, there are trapped ion approaches, there are a few others. That is ultimately a qubit, in some sense, operates like a synthetic or an artificial atom, right? How do you implement that? And so, looking at quantum volume, you can at least say, well, okay, with your type of qubit, what's your coherence time? How long is it around? Certain techniques are very good. They have long coherence times. Certain techniques have lower error rates. Certain techniques are completely imaginary right now, to tell you the truth. Yet people are, keep talking about it like they're going to have them real soon. Show me your hardware, first of all. Okay, they're probably, I would say, on the order of 6. The diamond dots and the range. Yeah, right around there. Different approaches. For us, we think our approach, which has to be cooled down close to absolute zero, offers the right balance, because you have to get to enough qubits, right? It's not enough to have a beautiful 2-qubit machine. And you can never get beyond, 2 qubits at room temperature. Well, that's lovely, but you're not doing anything with that, right? So ultimately, we need to scale into the hundreds and the thousands and probably the tens of thousands of qubits. We also haven't talked about error correction here at all, which is another question. Error correction gives you pure logical qubits. So if you read a textbook about what a qubit is and how it behaves, similar to what I talked about a little with the mathematics, those are logical qubits. They have a value, it will stay there forever. Right now, we estimate it would take at least 1,000 physical qubits like we have now to create one logical qubit. We have 50, right? And this is what I said at the very beginning, I don't care if we have 50 or 72 or 128. We need 1,000 just to get one logical qubit. So you're going to need tens of thousands of qubits to get to that point. And it's likely to take decades to do that. So yes, things will miniaturize because they always do. That's just what people do. We learn how to do more things off the shelf. If we have other technologies that can operate at warmer temperatures, that will shrink things down, as an example. But you have to scale, and that's when people are looking at the different technologies. How small can you make it, and can you get up to the hundreds of thousands of qubits?
Hey, so it's a bit of a specific question, but something I kind of came across for a project was related to the neuromorphic architecture and the quantum architecture converging. There's a particular component called a memristor, which essentially is a resistor that can have a bit of memory with how much current has passed through it. And if you apply that to quantum standards, a quantum memristor equivalent, and you can use this essentially as synapses between the neurons. So what are your guys' thoughts on how these two architectures potentially might converge and improve this in a more physical light, in order to potentially allow, qubits to still be able to maintain their superposition through this system, but also map a neural net in one-to-one instead of, have transistors simulate these neurons and synapses?
I think it's very interesting, but I think it's mostly theoretical at this point. You may be aware we've done some neuromorphic types of things. I don't think anyone in the world is really far advanced on, let's say, hardware for AI. There are a number of interesting approaches, but no huge breakthroughs yet on this. We're still at the point, frankly, of scaling up. So until we get to a few hundred qubits and have line of sight through that, I think there are other interesting techniques there. That is one. There are questions of just how close you can move classical components. Can you move some of them actually inside the fridge, right? So to operate close to absolute zero. And then you can start to get creative. I do think, so kind of generalizing the question a little bit, we're working on what are called universal quantum computers. So that is, it's a universal gate set. You have a universal gate set in your phone. That is, it's a Turing machine. So in the same way, it's not a special purpose way to do that. Nevertheless, as we look out for the next few years, there will be certain algorithms that are used more frequently. So variational quantum eigensolvers, the optimization algorithm. There are always going to be lots of other ones. But you might ask yourself to say, for a given algorithm, what is your ideal classical plus quantum architecture to do that? And so it may take, you'd still have a universal machine, it would be highly tuned for certain types of algorithms, whether search or whether things like that. So at that point, that might be interesting, but I think that's probably a second generation, so it would be more at the lower level, but I think for AI, these sorts of things. I would, generally for AI and quantum, by the way, I'd just like to say, I would love to see a program, sort of an academic program. A lot of the results are scattered. It's a little bit here, a little bit there, somebody's working on classification or something. Has anyone ever written down, like, this is what it really means? So here I'm thinking something like the big mathematical language programs and things like this. And over the next 15 years, we will work on these things to do this, that. But we're still a little bit more of an umbrella type of thing together. It'll come.
Well, I'm doing my best in that regard. So actually, I think it's the right time to plug that. I'm compiling the first massively open online course on quantum machine learning, trying to bring together the most relevant algorithms for shallow circuits, and also looking at some of the more abstract algorithms, just to see what you can do today and what you will be able to do in like 45 years. And I see it as a first step on providing foundations for further education and further research.
You're doing that through UT or Coursera?
It's going to be an edX.
Yeah, edX. You should let people know when it's available. Send to your mailing list.
It's going to be available. It's going to launch in February.
Great. Let me know.
So I have a question specifically about simulating quantum mechanics. from what I understand, so correct me if I'm wrong, like most of our, I guess, chemical simulations are based off the hydrogen atom, simply because it has one electron. It's very easy to solve for. So if we did, let's say, have a quantum computer capable of solving sufficient number of states, would that take into account electron-electron interactions in order to accurately predict those chemicals? Or would it just provide an approximation?
Yeah. Is that a question for me?
Yeah, mostly.
Okay. So the difficulty in simulating quantum mechanics is from the electron-electron interaction. Exactly. So if you take quantum mechanics in undergrad, you solve the hydrogen atom exactly,
Right.
and then helium atom you can't do. You basically use a variational solution for the helium atom.
Right, so would you say we're limited mathematically rather than from a quantum computation aspect in terms of the number of qubits we have?
Well, I guess the point is, like Bob said, in order to simulate n interacting electrons, the Hilbert space is 2 to the n. So that's the same exponential counting that he did.
Right. Sorry, what I'm getting at is, can we solve those, I guess, equations computationally rather than exactly just, on paper?
Yeah, so you can do the hydrogen atom exactly, and everything else you have to do computationally.
Okay.
Everything else, pretty much.
Okay.
But even doing it computationally is difficult because of that exponential, basically. Like, because of the fact that if you want to store, I don't know, whatever what's the biggest, caffeine.
Right,
If you
well,
want to,
it gives you an exact solution, right?
in principle, it could give you an exact solution, but the most you can do for electrons exactly is probably like 20, or if you have symmetry is 40 electrons or something like that.
Okay.
So that's computation.
So that's what quantum computing could potentially solve in 3 to 5 years.
Yeah, so some simulation techniques take advantage of approximations,
Yeah.
or inherent structures of, say, the wave function or the Hamiltonian that allow you to do thousands or tens of thousands or millions of electrons. But there's some cases that we don't understand how to do approximations for, and that's where we basically need quantum computers.
Got it.
Like everything in your iPhone is, in principle, quantum. It's all single electron, essentially, theory. And so, because the theory of metals and semiconductors is electrons that don't interact. So when you solve the hydrogen atom problem, or the equivalent, you can essentially solve the quantum mechanics for all of semiconductor physics. And so, what we're talking about, I guess, is when you have all these interactions, like you say.
Hi, thank you for this event. It's great being here. My question is related to the IBM business model, or the business behind IBM Cube. I was amazed about the IBM Cube network that is in place, and I wonder if for IBM, quantum computing means helping the world in some way and having an altruistic mission, or is thinking on being profitable at some point in time.
Being what?
Being profitable, to have profits.
Oh, yeah.
Yeah.
So I'm not going to tell you the planned business model, because that's confidential. But I will tell you some philosophy with respect to the business model. One of the things that has struck me is that even though we use many of the same words, in terms of computation, even developer communities and things like this, there really is a very broad and holistic view across quantum. Right? You need your theoretical physics, you have to make your devices, you have to work your cryostats and things like this. And so while there are intersections with classical computing, we all have, and not just IBM, we all have tremendous freedom to create almost a new industry here. Yes, they have to tie in. Right? Yes, they have to work together, workflows and things like this. But your business model does not need to be simply what you used to do. Right? It's not like, oh, that, but for quantum. And I used to see that. I mean, not naming names or anything like that. you'd see somebody like, we would have had a really successful product. And someone would say, let's just do that again, but for this. And then you'd say, well, that was like 18 years ago. Maybe things have changed. So the way we have approached this is to is to purposely not say it's just like one of these things we've done before, or IBM has always done such and such this way. And even something we did 5 years or so, to give ourselves the freedom to do that. I think it's very important, and again, I understand there are some entrepreneurs here thinking about this. You need an outside view. It's very easy to convince yourself what you think the right business model is. Well, timing. So while I threw out a few names, and there are other areas that we looked at as well, I didn't give you any timings. So I said, drugs work 10 years or something like this. But when will material science hit? Kind of going back to this, okay? When is that going to be important? So going back to how many electrons you can handle, things like this. We've talked about financial services, like risk analysis. What's the size of the inputs you can do, and when will we have that? What platform are you going to be on? So we're taking what I think is a very fresh approach here to do this, and give yourself that sort of freedom to do that. I'm sorry I'm not being very precise. It's just we've spent a tremendous amount of time on business model, so really not trying to answer it exactly. No, it's one of these things. But the philosophical approach is really, if the computer industry didn't exist, but you're as smart, and you were as smart as you are now, and I said, you get to create it all in the best possible way for 2019 and beyond, what would you do, and what would you absolutely avoid doing? Yet nevertheless, we see going up over and over again. Approach quantum that way.
No.
He was over there, so I did too.
You talked about different parts of the ecosystem having to come together to create this new industry. Where do you think startups in particular fit in that picture?
So we have lots of startups. D-Wave evidently is still a startup. They've been around since 1999. And they do a lot of interesting stuff. If you are a startup and your goal is to create a complete quantum computer, a whole quantum computer, plan on raising, I don't know, $150 million. Okay. Well, get going. It's pricey and it's hard. I mean, it's hard to do the whole thing. Right? And then related to that is the question of, if you're calling yourself full stack, well, what is your stack actually that you're so full of? Right? I think that there are some so thinking about this, at the control level, there's some very good startups. I think that at the standard component level, quantum limited amplifier and so forth, things like that, there'll be some very good startups. Because you have to assume that at some point, somebody's going to be making thousands of quantum computers. They're not going to bother when they're small. Once they get big enough, someone's going to make thousands of them. So that's who you're going to sell into. If you're only going to sell 12 of them, you're not going to do so well. There are a lot of people at the high-end applications, right? And there are a lot of people who hedge their bets. They say quantum and AI. And what do you really do? Well, we're really paying the bills with AI, right? Things like this. And there are also some people who say quantum, but we're going to put it on a GPU for now, right? and things like, you know what I'm talking about, right? So I guess the best advice, and this is a little, may sound a little strange, is if we look at the quantum startups that are out there, the very, very best ones have some of the top professors associated with them. So the top professors, physics professors, or AI, who have been in the industry, chemistry in some cases, who are joining startups, those are the best startups. And because they know what they're doing. They're not just hoping to come up with something clever in quantum. They have a mission. They know what they're doing. They have research they feel they can commercialize. Versus they love the name quantum and figure out it pays somehow, somewhere. So if you can't get them as a founder, you better have a very good advisory board of senior, respected faculty in those areas, and make sure they're going to be public for it.
Let me add to that, because I'm the academic director of the quantum program in the Creative Industrial Instruction Lab. So we are incubating a good 20 quantum startups every year. And I agree with everything that Bob said. So these caveats apply. And there is a 3 to 5 year timeline until we can do like fun stuff with these quantum computers, which is not trivial to simulate on a classical computer. But then, when you think about if you have just an AI startup and you want to go from zero to having a product or a service that you can actually sell, that's a good 2 years. And when you factor that in, that this 3 to 5 years doesn't look that scary anymore. So the actual gap between having something ready and getting some advantage in some quantum computer is not too bad anymore. So I think it's a good time to start exploring various ideas with startups and see whether some of these make sense and can be commercialized in the long term. But the timelines have to be realistic for the founders and also for the investors, because it's not an Android app that you can commercialize immediately. The timelines are much longer.
Just to add to that, I think another role for startups is, in some sense, almost offloading a lot of the applications work that would otherwise occur at say the companies like IBM, Microsoft, Google, and so on. If you have these really high quality APIs for cloud access into the devices, of course, it's almost better to farm out in some sense the applications to the startups, rather than trying to build an applications group in your own company, I presume, to try to explore all possibilities for problems, right? So I think that's one nice thing with all the sort of cloud APIs that are being built.
Before I got into quantum, within research I did some other things, and one of them was ag tech. And so I was at a conference in Silicon Valley, and one of the top name VC firms was there. And so there was this young entrepreneur saying, well, ag tech is going to take a while, right? Will the VCs have patience with us while we develop this and get it to market? The guy just looked at it and said, absolutely not. We're going to go to where we can get the fastest profits, sorry, right? So, as long as you have a day job or in school or something, or, parents, that's good, right? You can incubate it that way. But like Canada does, in Toronto in particular, I mean, you've got a great regional infrastructure for startups in quantum. I don't know any area that has as many quantum startups. The generalized Toronto area, which I don't know if it's insulting if I say word of that. I look at a map, sort of.
It's a kind of follow-up to the very first question when you mentioned about Moore's law. In Moore's law, we are relying on silicon. My question is in quantum computing, what we are relying to the most part from material perspective.
So it depends on how you build your qubits. So with us, they're Josephson junctions, so which are particular types of small analog devices. basically they kind of look like this, and they have insulators on both sides, and you can get essentially a non-linear oscillation where you can separate out between 0 and 1. So you basically can create a qubit there. But it is an analog device, so it's low-level software. But because it's so low-level, most people don't think of it as software, they just think of it as part of the silicon, right? But it really is. Now, in the same way with quantum devices, you have software, but it's not quite as separate. It is more separate than it is in the traditional cases. So we're learning a lot about doing error mitigation through both hardware and software. So those are the gating factors that we're looking at. And you can get huge improvements either way.
Maybe just for me and a couple other people, does IBM have a roadmap for error correction? And since you said 1001 mapping or something for logical qubits, are you guys still thinking about surface codes or topological?
We think about everything, but yeah, surface codes. No, I mean just in the sense of the department, sort of looks at all the way down surface codes and so forth. That's interesting. And by the way, what I said was 1,000. Other well-known people will say the number's closer to 10,000. Right? Because with these devices, actually going back to your question, you can only reduce the error rate so much. You can't completely eliminate it, and in fact, you can't even make it as small sometimes as you think you really want to. Now, there are some thresholds, and so related to surface codes being affected and so forth. As long as the error rate's below a certain amount, you're okay. It may increase the number of qubits you need, and so forth, and things like that. So that's what I was kind of saying. It's very tricky, this interaction in the qubit, but also among the qubits. It's much more complicated. So almost to the point where you have to stop thinking homogeneously. If you have a quantum computer with X qubits, I don't care what X is, right? There are going to be some fraction of that which are really good, and others which aren't quite as good. And for any number of factors, including manufacturing, but other things like this, are they contiguous? Are they not contiguous? What algorithms are you running? What can you use for some of these other ones? So it's a multi-dimensional problem, going back to our optimizing and pilot of how you map those things. So it's trickier. And also at the lowest level, I'm just going, so there are the classical silicon problems of crosstalk and so forth and things like this. But because you've got entanglement going on among qubits, quantum, let's just call them particles, whatever they happen to be, really want to entangle themselves with other things. Whatever else that's lying around. And so qubits will try to entangle themselves with each other, if they're too close, with, I presume, other quantum things in the neighborhood as well. So the problems are much trickier, and that's why sometimes when I'm being a little bit more shrill on Twitter, and I'm really trying to stop doing this. I sometimes say, like, if you're not building a quantum computer, you cannot project that something will happen, because it's trickier than you think. But your Moore's Law question is very good, because it encapsulates, what is your qubit technology, and what are these 12 factors for each of them, and how will that determine what you do?
Why don't we do one more, because it seems to be slowing down a little.
Yeah, this question's pretty general. I'm just curious, what is the most kind of, I guess, hacky, or what's the application of IBM Q that you've seen that surprised you the most?
Actually, I haven't looked at that many of them, so I couldn't get you. Let me just tell you though that so it's not application though.
So like usage.
Okay, well, this is slightly different, but so Ryan Mandelbaum, who writes for Gizmodo, for some reason, so he visited us, and we did this great big press day, right? So we invite them all to our research headquarters. We feed them well and we give them a tour, and we expect, let's be serious, you expect great articles saying how wonderful you are, right? That's what you hope for. Right? And he writes this article about dental floss because he was walking around the lab and saw a spool of dental floss. And like, what the heck is going on? I mean, you've got these $1 million computers and you're tying them together with dental floss? And so he immediately called up like John Martinez at Google and a couple of other people. And everyone said, oh yeah, we all use dental floss in the quantum computers. And it turns out that, so non-waxed, non-flavored dental floss is very good. You can freeze it down to absolute zero and it doesn't get brittle. And so you can occasionally tie things up on the inside. So that's the total most surprising thing I've ever seen. Thank you. Okay?
Great. Thank you so much. Let's join me to thank our great speakers. And Dr. Peter Meeting, thank you so much for having and staying so long with this weather.
Yeah, hope you get home, drive safely.
Please drive home safe, yes. I think we still have pizza.
There's only 3 more inches since you arrived.
Yes. Welcome to Canada.
Thanks, Reza.
Thank you.